Good afternoon, everyone. Welcome to lecture. In today's lecture, we're gonna talk about the shear strand of soil. Here we go. The shear strand permits soil to remain in its place on a hillside or in an earth dam or embankment as illustrated in the figure. Additionally, it decreases soil pressure acting against retaining wall, and it is responsible for the bearing capacity of shallow and deep foundations. The shearing strength of a soil as its resistance to shearing stress, which may be caused by an external load such as a foundation or by the weight of the soil itself, such as a slope weight. When the shearing stress surpasses the shear strength of soil, soil will shear, bringing about the formation of shear slip surface as shown in the figure here, over which a huge sliding movement may occur. As a result, slope failures such as landslides can lead to significant economic loss to local communities. For that reason, an understanding of shear strand is a basis to the behavior of a soil mass. In this regard, let us go through the behavior of two groups of soils, namely type 1 and type 2, when they are subjected to shearing forces. Type 1 soils are categorized as loose sands, normally consolidated and lightly over-consolidated clay soils. Type 2 soils, on the other hand, are classified as dense sands and heavily over-consolidated clay soils. In the figure here, a typical response of those soils to shearing at a constant normal effective stress is given as a relation between shear stress and the shear strain. In the figure, you see some definitions as peak shear strength, critical state shear strength, and residual shear strength, depending on the soil type and condition. Let us a bit elaborate what they are. In loose sand, normally consolidated and lightly over-consolidated clays, the shear strain increases as the shear stress increases until about constant shear stress, which is called the critical state shear stress, is obtained. On the other hand, in dense sand and over-consolidated clays, shear stress increases very quickly, attaining a peak value at low shear strains with respect to type 1 soils, and then decrease with increasing shear strain, eventually reaching a critical state shear stress. This phenomenon would also apply to a soil which has developed cementation or chemical bonding due to deposition. In some types of over-consolidated clays, the particles orient parallel to the direction of the shear band, causing the final shear stress of these clays to decrease below the critical state shear stress. This final shear stress is called the residual shear stress. Now, the question is, which one of these shear strengths matters then? Peak shear strength is the maximum shear stress which can be experienced. It may be risky to rely on this value for some brittle soils owing to the rapid loss of strength if the soil is strained beyond this point. Critical state strength is sometimes regarded as the ultimate strength. After a considerable amount of shear strain, a soil will attain a constant volume state, and it will continue to shear without any change in volume or void ratio, but the strains and movements of the earth structure, such as foundation, slopes, etc., will be so large that they could be considered to have failed. Therefore, a maximum strain limit must be adopted, usually related to the performance of the earth structure. Let's say 10 or 20% of strain of the ultimate strand may suffice. After a considerable amount of strain on a single slip surface, the particles either side of the surface will rearrange to produce a more parallel orientation, and this will cause the lowest possible strength. This strength is very important in the reactivation of old landslides, and it's obviously more significant for platy minerals, for example, clays. Are there some other factors that may affect the shear strength of soils? Yes, there are. One of them is normal effective stress. The higher the normal effective stresses are, the higher the critical state shear stresses. Another factor is the overconsolidation ratio. Higher overconsolidation ratios of homogeneous soils bring about higher peak shear stresses. And drainage condition is an effective factor as well. The shear strengths of saturated fine-grained soils under drained condition are higher than those of saturated fine-grained ones under undrained condition. Cohesion, which is the shearing resistance from intermolecular forces, but they are generally small. Soil suction, which results from the surface tension of water on soil particles in unsaturated soils, generates an apparent shear resistance that vanishes when the soil is saturated. Cementation is due to chemical bonding, such as calcium carbonate of soil particles. Finally, size, shape, and gradation of granular soils. As the particle size increases, the shear strength of granular soil increases as well. Angular particles cause higher strength than that of rounded particles. In addition, well-graded soil will produce better interlocking and have more interparticle contacts, causing higher shear strength. The shear strength of a soil can be either determined in the laboratory or in the field. Two types of test, namely direct shear test and triaxial compression test, are primarily used in the laboratory. The shear box test equipment basically made up of a metal shear box where the soil sample is placed as you see in the figure. The soil samples may be square or circular in plan. We have a square type one here. The box is split horizontally into two halves. Normal force on the soil sample is applied from the top of the shear box through a loading frame using dead weights, and the shear force is applied through a motor running at a constant rate to the side of the top half of the shear box to cause soil sample to fail. Here, we just briefly explain the main points of the test. You can find the details in the related manuals. In order to determine the shear strength of soil, a series of shear box tests are carried out in the laboratory. During these tests, the normal force is vertically applied to the soil specimen, as mentioned earlier, and kept constant throughout the test. The shear force is then applied in steps, and the corresponding values of shear strains are recorded and plotted as shown in the figure here. The peak and the residual shear stresses in each test are gathered and analyzed in terms of the maximum shear stress against the normal stress. The results of 4 shear box tests are given in the figure here. The line which joins the experimental points is named as the strand or failure envelope, as you know. It shows the maximum strength of soil at failure, and it is mathematically defined as shown in the equation. In this equation, C is the cohesion intercept, phi is the friction angle of soil, and sigma is the normal stress. This equation is known as the Molclum failure criterion. It provides the maximum shear stress that soil can bear without failure. It is generally assumed that for coarse-grained soils, cohesion intercept is zero. So this type of soil is referred to as cohesionless soil, and the above equation can be reduced to the equation given here. It is mentioned that there are some inherent drawbacks of the direct shear test. What are they? First of all, the soil is forced to shear in a predetermined plane. That is to say, the horizontal plane is not certainly the weakest plane. And secondly, there is not uniform stress distribution over the shear surface. The stress is greater at the edges than at the center. This type of stress distribution brings about progressive failure. And finally, it is impossible to control the drainage from the sample or to measure the pore water pressure within the sample. The most trustworthy method extensively used for the determination of shear strength parameters of soils is the triaxial compression test. In the figure here, you see the details and the setup of triaxial compression test. In this test, a soil sample about 38 millimeter in diameter and 76 millimeter in length is commonly used. The sample, enclosed in a thin rubber membrane, is placed inside a plastic cylindrical chamber, also known as perplex cylinder. To run the test, the chamber is filled with water and the soil sample is subjected to all-round pressure. In other words, a confining pressure by the application of pressure to the water in the cylinder. Now, to fail the sample, the deviator stress is applied through a vertical loading ram at a constant rate of axial deformation, and the axial load corresponding to any given axial deformation is measured by a proving ring which is connected to the loading ram. In triaxial tests, the soil specimen is first consolidated under an equal all-round pressure. The all-round pressure, which is denoted sigma sub 3, is also known as the cell pressure, confining pressure, or chamber pressure, whichever you like. The axial stress is then applied till the specimen fails. The deviator stress, which is equal to the difference between the principal stresses, is commonly used to define the stress conditions at failure. Experimental data from triaxial tests are analyzed by plotting the Mohr circles for stress conditions at failure, as you see in the figure. Each Mohr circle represents 3 identical samples subjected to 3 different confining pressures. To ascertain the shear strand parameters, namely C and phi, C stands for cohesion intercept and phi stands for internal friction angle, the failure envelope or strand envelope, whichever you like, which is a tangent line to the circle, is drawn as shown in the figure. The point of intersection between the failure envelope and the tau axis, which is vertical axis, gives the value of cohesion intercept, while the failure envelope inclination defines the internal friction angle of soil. There are 3 types of triaxial tests that are commonly used. The first one is consolidated drained test, and the second one is the consolidated undrained test, and finally, the third one, unconsolidated undrained test. The purpose of consolidated drained test is to determine the drain shear strength parameters to analyze long-term loading of a soil mass. The sample is first subjected to a confining pressure through the pressurized water in the cylinder. Because of the confining pressure, the pore water pressure of the soil sample will increase. Since the drainage is permitted, the pore water pressure generated will dissipate and becomes zero. In saturated soil, the change in volume of sample during consolidation can be figured out from the volume of pore water drained. After the application of confining pressure and the dissipation of the related excess pore water pressure, the deviator stress is then applied to the sample at a very slow rate. The drainage valve is kept open, and the slow rate of deviator stress application permits complete dissipation of pore water pressure generated during this stage. Since the pore water pressure generated during the test is completely dissipated, the effective stress is equal to total stress, and the load is transmitted to the specimen by the soil particles. In a triaxial test, sigma 1 prime and sigma 3 prime are the major and minor principal effective stresses at failure. Several tests on identical samples can be carried out by varying the confining pressure. With the major and minor principal stresses at failure, for each test, more circles can be plotted and the failure envelope can be obtained. This figure here indicates the type of effective stress failure envelope obtained for tests in sand and normally consolidated clay. In this test, to calculate the deviator stress, the net axial load should be divided by the cross-sectional area of the sample, since it does not remain constant throughout the test. For this reason, the volume change during testing needs to be known. If V sub 0 is the volume of the sample at the beginning of the test, and delta V sub C and delta V sub D are the changes in volume after the application of confining pressure and deviator stress respectively, then the cross-sectional area can be obtained by the equation given here, where some delta V is the total volume change of soil sample, which is equal to delta V sub C plus delta V sub D. And delta V sub C is the volume change due to confining pressure. Delta V sub D is the volume change due to deviator stress. Some delta H is the total change in the height of soil sample, which is equal to delta H sub C plus delta H sub D. Delta H sub C is the change in the height of soil sample owing to the confining pressure, and delta H sub D is the change in the height of soil sample owing to the deviator stress. And finally, H sub 0 is the initial height of soil sample before testing. The aim of consolidated undrained triaxial test is to determine the undrained and drained shear strength parameters of soil. In these tests, the soil sample is first consolidated by confining pressure, and drainage from the sample is permitted. After complete dissipation of excess pore pressure developed by the confining pressure, the deviator stress is applied to the sample and increased until the soil fails in shear. During this stage of the test, the drainage line from the sample is closed. Therefore, the pore water pressure will increase. Concurrent measurements of deviator stress and the related excess pore water pressure are made during the test. In contrast to CD test, the total and effective principal stresses are not the same in CU test. Since the pore water pressure at failure is measured in this test, the principal stresses may be analyzed as follows. The total major principal stress at failure is equal to sigma sub 1, which is equal to the expression given here. And the effective major principal stress at failure is equal to sigma sub 1 prime, which is equal to the expression given here. The total minor principal stress at failure is equal to sigma sub 3. The effective minor principal stress at failure is equal to sigma sub 3 prime, which is equal to this expression given here. In these definitions, delta U sub dF is the pore water pressure at failure. Tests on several identical samples with varying confining pressures may be made to determine the shear strength parameters. The figure on the following slide indicates the total and effective stress Mohr circles at failure obtained from CU tests in over-consolidated clay. In the figure, notice that A and B are two total stress Mohr circles obtained from two tests. C and D are the effective stress Mohr circles corresponding to total stress circles A and B respectively. The diameters of circles B and D and A and C are the same. CD tests on clay soils take considerable time. Therefore, CU tests may be conducted on such soil with pore pressure measurements to obtain the drained shear strength parameters. Since the drainage is not permitted in these tests during the application of deviator stress, they can be carried out rather quickly. In consolidated undrained test, to calculate the deviator stress, net axial load should be divided by the cross-sectional area of the soil sample. The cross-sectional area can be obtained by the equation presented here, in which V sub 0 is the volume of soil sample at the beginning of the test. H sub 0 is the initial height of soil sample before testing. Delta V sub C is the volume change of soil sample owing to the confining pressure. Sum delta H is the total change in the height of soil specimen, which is equal to delta H sub C plus delta H sub D. Delta H sub C is the change in the height of soil sample owing to the confining pressure, and delta H sub D is the change in the height of soil sample owing to the deviator stress. The goal of unconsolidated undrained test is to find out the undrained shear strength of a saturated soil. In this test, the drainage from the soil sample is not allowed. The confining pressure is first applied to the sample, and then the deviator stress is applied to cause the soil sample to fail in shear. Since the drainage is not permitted at any stage, the test can be conducted very rapidly. Since the drainage is not allowed from a saturated test specimen, any increase in total stress brings about an equal increase in pore water pressure, which leaves the effective stress unchanged. If two or more identical saturated soil samples are tested under undrained condition at different confining pressures, they will fail at the same deviator stress. In this case, the total Mohr circles have the same diameter and the failure envelope has zero slope as shown in the figure. Let us justify what we have just said. Now, for the first case, for the first sample, if we define the effective confining pressure, which is sigma prime sub 31, as equal to sigma sub 31 minus U sub 1. U sub 1 is the excess pore pressure developed due to confining pressure applied to the sample under undrained condition. And the second test for the second sample, if the confining pressure is increased by an amount of delta sigma sub 3, the excess pore pressure will be increased as well, which is equal to U sub 1 plus delta U. Delta U is the excess pore pressure increase due to delta sigma 3. We know that any increase in total stress will produce the same amount of increase in excess pore water pressure under undrained condition. For that reason, the effective confining pressure for the second test or for the second sample can be defined as shown here, which is equal to confining pressure for the first sample. That's it. Therefore, if identical samples 1 and 2 are forced to shear by increasing the axial stress, they ought to fail at the same deviator stress. In this test, for the calculation of deviator stress, we need the cross-sectional area of the soil sample. Since there is no drainage at any stage of the test, there will be no volume change. Therefore, the cross-sectional area of the sample during undrained unconsolidated test can be obtained using the equation presented here, where V sub 0 is the initial volume of soil sample just before testing, which is equal to A sub 0 times H sub 0. A sub 0 is the cross-sectional area of soil sample at the beginning of test. H sub 0 is the height of soil sample at the beginning of test. Sum H is the total change in the height of soil sample. The objective of unconfined compression test is to work out the undrained shear strength of saturated clays quickly. It is a special type of undrained unconsolidated test and generally used for clay samples. In this test, the all-round pressure is 0. The axial load is then applied quickly so that the pore water cannot drain from the soil. The sample is sheared at constant volume, so at failure the total minor principal stress is 0 and the total major principal stress is sigma sub 1. The question is, what type of triaxial tests, drained or undrained, is more advantageous? Well, the undrained test has the advantage of providing the strength characteristics of soil under both effective and total stress conditions, while the drained test does not provide any data about the excess pore water generation. And the second question, what are the advantages of triaxial test or direct shear test? Unlike the direct shear test, the shear failure planes of soil specimens are not predetermined in triaxial tests. The triaxial test provides a greater ability to control and know stress conditions on the specimen with respect to the direct shear test. From the discussion of different types of triaxial tests, it is obvious that the shear strength of soil depends on the pore water pressure produced during loading. The pore water pressure dissipates with drainage. For field conditions, the shear strength of soil therefore depends on the rate of application of the load and the drainage. In field conditions, a granular soil is probably to have full drainage if the rate of load application is moderate. Then the drained shear strength parameters will take control. On the contrary, for normally consolidated clays, the time needed for dissipation of pore water pressure resulted from construction may be too long. An undrained condition may govern during and immediately after construction. Therefore, the phi-0 conditions may be more suitable for use. Shear strength of unsaturated soil, in other words, partially saturated soil, is a function of the related effective stresses. But it is very difficult to apply the principle of effective stress because of the parameter chi in the equation given here. When the expression for sigma prime is replaced into the shear strength equation, we get the equation in the form given here, where U sub A is the pore air pressure, U sub W is the pore water pressure, U sub A minus U sub W is the matrix section, and chi is a parameter depending on the degree of saturation. So, for fully saturated soil, chi is the unity, and for dry soil, it's equal to 0. Effective stress parameters can be obtained from a series of CU tests with pore water pressure measurements or CD tests on specimens fully saturated by the application of back pressure. Total stress parameters may be determined from a series of unconsolidated undrained tests on soil specimens. The undrained shear strength increases with increasing confining pressure, as you see in the figure. But the shear strength increase becomes progressively smaller as the void ratio is reduced due to compression of pore air. Follow the dashed line in yellow and you understand what I mean. Now, when the confining pressure attains a high enough value, all the pore air will be forced into the solution in the pore water and the failure envelope become horizontal with phi-0. The curve with failure envelope can be approximated to a straight line as illustrated in the figure, or the stress range of interest and values of C sub U and phi sub U are obtained. Disturbances of soil samples during recovery from the field and sample preparation for laboratory tests may considerably weaken the shear strength parameters. As a result, a variety of field tests have been produced to obtain more reliable shear strength parameters by testing soils in situ. The most frequently used ones will be very briefly explained here. One of them is the vein shear test. It is used for the in situ determination of the undrained shear strength of non-fissured, fully saturated clays. Therefore, the test is not suitable for other types of soil. The vein, as you see in the figure, and the rod are pushed into the soil from the bottom of a borehole to a depth of at least 3 times the borehole diameter. The torque is then applied gradually to the upper end of the rod by means of a suitable equipment, as you see in the figure, until the clay fails in shear due to rotation of the vein. The undrained shear strand is then worked out from the expression presented here. Very well known in situ test is called Standard Penetration Test, SPT for short. This test is carried out by driving a standard split spoon sampler, as you see in the figure here, into the ground by blows from a drop hammer of about 63.5 kilogram, falling free from a height of 760 millimeter. The sampler is driven 15 centimeter into the soil at the bottom of a borehole, and the number of blows needed to drive it an additional 30 centimeter is counted. The number of blows is called the standard penetration number. Different corrections are applied to the N values to take into account energy losses, overburden pressure, road land, anvil, and so on. The corrected number of blows have been associated with several soil parameters. Most of these correlations are weak. Typical correlations among N values, relative density, internal friction angle, and undrained shear strands are presented in the following tables 1 and 2. One should be very cautious in using these correlations. Table 1 shows a relation between standard penetration number, relative density, and internal friction angle for coarse-grained soils. And Table 2 presents a relation between the corrected standard penetration number and the undrained shear strand for saturated fine-grained soils. It is important to note that SPTs are not recommended for fine-grained soils, so the correlation given in Table 2 should only be used to give an assessment of the relative shear strength of fine-grained soils. Finally, another popular in situ test is called Cone Penetrometer Test, CPT for short. It has a cone with a base area of 10 square centimeter and a cone angle of 60 degrees attached to a rod. The rod is included in the outer sleeve. The force required to drive the cone and the sleeve into the ground at a rate of 2 cm per second are measured independently so that the end resistance and the side friction may be assessed separately. The cone resistance is normally correlated with the undrained shear strength. Several correlations are made to cone resistance. One of them is as follows, where N sub k is a cone factor which depends on the geometry of the cone and the rate of penetration. Sigma sub z is the total stress at depth z. Average values of N sub k as a function of plasticity index can be estimated from the expression provided here. Practical example 1. You, as a geotechnical engineer, are in charge of analyzing the possible failure of a natural slope composed of homogeneous soft clay by a rotational slip surface, as you see in the figure. What laboratory tests would you specify for these cases and why? Short-term and long-term stress state conditions along the failure surface should be taken into consideration. Nevertheless, the undrained condition, which is the short-term condition, is the most critical one because the shear strength of soil increases while the drainage takes place. So the recommended tests are undrained unconsolidated or consolidated undrained triaxial tests or direct shear box tests. And the parameters needed are cohesion intercept and the internal friction angle. Practical example 2. To estimate the stability of the sand embankment, 2 samples were collected. One of them was taken from the embankment and the other from the saturated clay soil layer. A series of shear box and consolidated drain triaxial tests were conducted on these soil samples, and the acquired data are presented in tables 3 and 4 as follows. Now, you are asked to plot the obtained results and determine the shear strength parameters of sandy and clay soils needed for the slope stability analysis of embankment along the failure surface. In the solution of these problems, the first step is to compute the normal and shear stresses and tabulate them. This is already done for you as you see in the table, but I will show you how to calculate the normal and shear stresses. For example, for test 1, the normal stress is defined as the ratio between the normal force and the soil specimen area, which is equal to 75 kilonewton per square meter. Similarly, the shear stress is defined as the ratio of the shear force and the soil specimen area, which is equal to 40 kilonewton per square meter. The same procedure is carried out for the calculation of normal and shear stresses for each test. It is important to note here that the cross-sectional area of soil specimen for the calculation of normal and shear stresses as the same. And the second step, the normal and shear stresses from the table are used to draw the failure envelope to determine the shear strength parameters of sandy soil as shown in the figure. Since the tested soil is sand, its cohesion intercept will be zero. So the failure envelope will pass through origin, making a certain angle with the horizontal. The failure envelope results in the friction angle of 28.6 degrees and zero cohesion intercept. In the third step, the Mohr circles for each test using the data provided in Table 4 are plotted, and the failure envelope is drawn, and the values of cohesion intercept and the friction angle of clay soil are determined. The failure envelope brings forth the friction angle of 9.4 degrees and cohesion intercept of 37 kilonewton per squared meter. Practical example 3. A rectangular foundation of 4 meter times 5 meter applies a total load of 6 meganewton to a deep uniform deposit of normally consolidated clay with the coefficient of earth pressure of 0.41. Groundwater table is at 0.5 meter just below the foundation base. The UU test, which is unconsolidated undrained triaxial test, was run on a soil sample taken from a depth of 4 meter below the foundation center. The determined shear strength parameters, namely Cu and Φu, are 40 kilopascal and 0 respectively. The question is to determine if the soil will reach the failure state for short-term condition or not. And the solution of this problem, the first step is to compute the initial stresses at a depth where the sample was taken. This is an easy job since we know the unit weights and the thicknesses of soil layer. So the vertical stress, in other words, the major principal stress can be obtained as 92 kilonewton per square meter. And the minor principal stress, which is sigma 3, is a function of major principal stress, obtained by multiplying major principal stress by K0. K0 is the coefficient of lateral earth pressure at rest. In this way, the minor principal stress can be obtained as 38 kilonewton per square meter. The second step is to calculate the vertical stress increases at 4 meter under the center of foundation. To do this, we generally use Bosch-esque equations. Initially, we calculate the parameters R sub 1, R sub 2, R sub 3, and Q needed for the equation. R sub 1, R sub 2, and R sub 3 are dependent on length, width of foundation, and the depth under consideration. Q is the foundation pressure, which is obtained as a ratio between foundation load divided by the foundation area. Now, having all the values calculated and putting them in their relevant places in the equations, we can get the vertical stress increase, the horizontal stress increase, and the shear stress increase as illustrated. In the third step, the imposed shear stress for short-term loading is computed. Current vertical total stress is equal to major principal stress plus the vertical stress increase. Similarly, the current horizontal total stress is equal to minor principal stress plus the horizontal stress increase. And finally, the current total shear stress is equal to present shear stress plus the shear stress increase. The present shear stress can be obtained by the expression provided here, which represents the radius of Mohr circle under undrained condition. Just remember the case for undrained, unconsolidated triaxial test. The total shear stress can be obtained and then compared with the shear strength of soil under undrained condition. Since the total shear stress is greater than the shear strength of soil under undrained condition, the soil mass will fail. Now, it is a quiz time. Let us recap the main points we have learned so far. The first question, drain triaxial compression test means the soil specimen is dry. True or false? Yes, you got it. The answer is B, false. Good. The second question, what is meant by the shear strength of soils? Be careful. Which one? No. Another option? No idea? Okay then. The answer is A, resistance to shearing stress. And the third question, the term back pressure used for triaxial compression tests means a bit tricky one. Which one? No. No, it is not. Yes, you are right. The answer is C, pore water pressure. Keep going. Question 4. There is no volume change of soil under UU triaxial test. UU stands for undrained, unconsolidated. Which one? No, you got it wrong. The answer is A. It's true because there is no drainage at both stages. So be careful. If there is no drainage, there is no volume change. Sample may deform laterally, but the volume will be kept constant. Question 5. Soil states above the peak shear strength boundary are impossible. True or false? Which one? No. The answer is A. It's true. And the question 6. Cementation imparts shear strength to the soil at zero normal effective stress. Yes, you got it right. The answer is B. It's true. And the question 7. Under what condition should the undrained shear strength parameter be employed? Who said none of them? There's no option like that in the question. You must be kidding. Which one? I'm sorry, it's not. The answer is C, for short-term loading. Question 8. All soils reach a critical state, irrespective of their initial state, at which continuous shearing occurs without changes in shear stress and volume for a given normal effective stress. True or false? Now, before jumping to answer, read the question carefully and then give your answer. Which one? No, it is not. Which one? Yes, the answer is true. Tell me, did you get it by chance or by choice? Be honest to me. By chance. Okay then. Now, the question 9. At large strains, the particles of some over-consolidated clays become oriented parallel to the direction of shear bands, and the final stress attained is lower than the critical state shear stress. Is it true or false? No idea? Okay, let me give you the answer. The answer is A. It's true. And the final question. Soil tension resulting from surface tension of water on soil particles in an unsaturated soils creates an apparent shear resistance. True or false? Which one? Yes, you got it. The answer is A. It's true. That's all. Well, we've come to the end of this lecture. Thank you for listening. Hope to meet you again. All the best.